Okay, welcome back, everybody. So, we left off yesterday with the following question. So, what about Laplace's equation? So specifically, what about applying our separation of variables to Laplace's equation? I.e., what about the separation of variables algorithm applied to Laplace's equation, right? Laplacian of u is equal to 0. Okay. So as I mentioned yesterday, the thing that's a little different here is that since Laplace's equation doesn't involve a time variable, the kind of equivalent formulation of Laplace's equation compared to the PDEs, the two others of the big three that we've done so far, which the solution we found depended on x and t, right? A solution we find to this is going to depend on x and y here. So this is going to have two spatial variables, which means that a boundary value problem is going to involve a boundary that is a one-dimensional set rather than two endpoints on a 1D interval, right? So the boundary of a 2D set, the 2D region in the plane, is going to be some curve generally, right, for most of the regions that you've seen. And so this is a more complicated thing. And so the answer is let us consider a couple of different examples for specific 2D regions. So the first one is Laplace's equation in a rectangle. So example, Laplace's equation in a rectangle. So we can, just like we did with our 1D bar, right? We put one end at the origin. So here we have Laplace's equation on some two-dimensional region, some rectangle. I might as well put one of its vertices at the origin. So we'll put its bottom left vertex at the origin here. So we'll have a rectangle that looks like this. Okay, so here's my rectangle. We'll call it R. So here's my region R. We'll say that X goes from 0 to A, and Y goes from 0 to B. So this region R is a product of two closed intervals. Okay. And so what would boundary conditions look like, right? Well, what is the boundary here? Let me pick a different color. So what's the boundary in this case? The boundary is 4 pieces. Now you might say, well, can't I just consider them all together? It's a curve, right? Yes, it is a curve. It's a piecewise continuous or a piecewise smooth even boundary broken up into these pieces here. And of course, you might remember from Calc 3, whenever you had a boundary like this, right, typically the way that you dealt with it was you dealt with it on the pieces, right? Because there's corners here for a variety of reasons. Maybe I want to avoid talking about corners. And so, there's a lot to be said about what to do to deal with such things. But what about breaking it into 4 pieces, right? So 4 pieces. There's the left piece, bottom piece, right piece, and top piece. Well, on each of those pieces, I could prescribe a different boundary condition, right? Of course, I could describe, say, like maybe uh, a like homogeneous, right? It's all 0 on these pieces, and you can consider, once we've done this, you can consider what that would lead to necessarily. But if we're talking about like a general Dirichlet problem where we have a value on our solution u, right, on this boundary, then the most general thing is that on each piece, the value of my function u is given by some different data function, right? So, for instance, so let's say we seek a u xy that solves the following problem on R, right? And so u sub xx plus u sub yy is equal to 0 when we're on the interior of the rectangle. This is x strictly between 0 and a, y strictly between 0 and b. Okay, so we wanted to solve Laplace's equation on the interior of this region. And on the boundary, we prescribe boundary conditions. The completely general case would be u of x 0. So when y is 0, that's this bottom piece, then this is some function f sub 1 of x. When y is b, so that's the top, u of xb is some function f sub 2 of x, and this is for x between 0 and a. And on the left, when x is 0, so u of 0 y is some other function of y, f sub 3 of y. And on the right end, so u of ay, this is some other function, f sub 4 of y, and that's for y between 0 and b. Okay. So a very, very quick way of rewriting this, right, is to write it as the following, right? This is Laplacian of u is equal to 0 on R, or the interior of R, really, but don't worry too much about that. Okay. And u is equal to some g on the boundary of R, right? Where the boundary of R is this part that I've shaded red here, right? Now you might say, wait, right? What are you... Here you wrote it as a single function, right? But it's clear in this picture, or in this case, right, that this is multiple functions here. Well, these could be thought of as a single function by saying that this is a single function that is piecewise defined, right? On each of these pieces, these are its constituent parts. Okay, so I could wrap those up in a single function, but of course, if we're going to actually be computing with these things in this example, it's going to be easier to deal with things like this. Okay, in fact, you might have already noticed that by superposition, it's actually going to suffice for me to consider a slight modification of this problem where these functions are substantially simpler, right? Or at least most of them are. Okay. And so, consider for a second how this problem can be written in a compact form as this thing. And it's clear now because we have a PDE that's being satisfied on region, and then we have some boundary condition, on the boundary. This is a BVP for Laplace's equation, right? And in fact, because we're prescribing the value of u, the solution we seek on the boundary, this is in fact a Dirichlet BVP for Laplace's equation. Now, I mean, this is what a Dirichlet BVP looks like for Laplace's equation, regardless of what R is, but in this particular case, this R is a rectangle. Now, you might say, what's the context for Laplace's equation, right? I forget. So recall that kind of one of the easiest ways of motivating this is to note, oh, well, this is kind of like one side of the heat equation if u sub t is 0, right? So this is like a solution to this is going to be like an equilibrium or steady state heat distribution in a rectangle, right? So if I thought of now a 2D heat equation, right? If I thought of a 2D heat equation, maybe let's write this on second sheet. So recall the 2D heat equation. So this is u sub t is equal to Laplacian of u, or in the 2D case, this is u sub xx plus u sub yy. Then equilibrium, or steady state solutions satisfy u sub t equals 0. So if u sub t is u sub xx plus u sub yy, this means that for equilibrium solutions of this thing, I must have this, right? And so another way of thinking about this is that this is solving for equilibrium solutions. Now you're one dimension up, right? This is for the 2D heat equation. Okay. This is one way of motivating this. There's plenty others, but that was one way that we mentioned. Okay. So the first thing we do, the first thing we notice, if I call this asterisk, all right, this BVP here, then asterisk can be solved by first solving for different BVPs. Okay. All of these BVPs look like this. What? Well, they satisfy Laplace's equation on the interior. Okay. And they have boundary conditions that are 0 everywhere except on one piece. So 0 on the bottom, 0 on the top, and that's x between 0 and a. 0 at the left end, and on the right end, non-zero. Okay, let's compare. So all I did here is I zeroed out all of these functions except for the last one, right? The one on the right end. Okay, that's the only one I didn't zero out. Now, why do I say that I can solve this by first solving 4 different BVPs and all of them look like this? Well, it's clear what I'm talking about here is I could solve a BVP where f sub 1 is the only one that's non-zero. So f sub 1 is generic, and f sub 2, f sub 3, and f sub 4 are all 0. So 0 everywhere except on the bottom, and then we could consider 0 everywhere except at the right end, which is what we have here. And then we could consider 0 everywhere except on the top, which it would be f sub 1, f sub 3, and f sub 4, 0, right? And f sub 2, generic. And then we consider the BVP where it's 0 everywhere except at the left end, which, oh, I already did that. No, I did the bottom first. Left end, that would be everything 0 except f sub 3. And once I have found a solution, right? So this would yield solutions. So these solutions would be u sub 1, xy, u sub 2, xy, u sub 3, xy, and u sub 4, xy. So each of those would solve a corresponding BVP like this, where for u sub 1, we could make the notation such that f sub 1 is the only non-zero thing here. Right? So f sub 1 is the only non-zero thing. All the others are 0. Same thing for u sub 2, u sub 3, u sub 4. Once we have that, then our solution to asterisk is u equals u sub 1 plus u sub 2 plus u sub 3 plus u sub 4. I could just sum those 4 solutions. Again, this is principal superposition, right? So just quickly check. Laplacian is linear, and so the Laplacian of u is the Laplacian of u1 plus u2 plus u3 plus u4. So that's Laplacian of u1 plus Laplacian of u2 plus Laplacian of u3 plus Laplacian of u4. All those are individually 0, so this is 0. So this definitely solves Laplace's equation. And notice that on the boundary, right, so if we restrict u to the boundary, right, so we have to look at what u is on each piece, right? So let's check here. On the left end, right, when x is 0, on this left end, this thing is, all of these are 0, right, except u sub 3, which is f sub 3. So on the left end, it would be f sub 3. On the bottom, all of these are 0 except u sub 1, which is f sub 1, so it would be f sub 1. And so on the right, all these would be 0 except u sub 4, which is f sub 4 there, so it's f sub 4 on the right end. And at the top, all of these are 0 except f sub 2, or u sub 2, which is f sub 2 on the top. And so on each of these pieces, u is equal to what it should be. So this is equal to exactly each of these f sub 1, f sub 2, f sub 3, and f sub 4s where it should be on the boundary. Okay? And so, actually, I only need to solve a boundary value problem that looks like this. And if I can do that, then all I have to do is the corresponding problems where I've zeroed out the 3 others for each of these slots. And then I sum the result to get the absolutely general solution to this. Okay. Now, what we're going to do is we're going to do this one. In your homework, you're going to do the one where this function is non-zero and the others are 0. So you will do one of these in your homework, and this is actually a really good exercise for this stuff, is basically practicing by solving each of these 4. We're going to do this one. You're going to do this one in your homework, and you can try the other 2 as well to see how this works. Okay. And so, So for now, let us solve the following. So this is, we'll call this star. So u sub xx plus u sub yy is equal to 0 on the interior of the rectangle. Okay, u sub x0 is 0, u sub xb, or not sub, u of xb is 0, and this is for all values of x. And at the left end, this is 0. At the right end, we actually have a generic function. So u of a y is, I'm just going to call it f of y here, right? No need to worry about subscripts now, okay? And this is for y between 0 and b. So this is what we're going to solve, noting that to solve the original thing we wanted to, we would need to solve a problem like this for each of these slots, so having an f of y in each of these slots with everything else 0, and then sum those four, okay? So as before, now we have separation of variables. So we seek our solution u of xy to be a product x of x, y of y. Okay. And we're seeking a separated solution like this for the PDE. So we seek this, which is a solution to PDE plus homogeneous boundary conditions. Right? So immediately from the PDE itself, right? So uxx plus uyy equals 0. What does that mean for this separated solution? It means that x double prime of x times y of y plus x of x times y double prime of y is equal to 0, which leads me similarly to a statement x double prime of x over x of x is equal to, I'll put the minus sign over here, minus y double prime of y over y of y. This holds for all x and y in the interior. Right, so this is for all x strictly between 0 and a, and y strictly between 0 and b. Okay. Well, the only way that this equality can hold, because the left-hand side depends only on x, the right-hand side depends only on y, is if these are both equal to the same constant. Right? So as before, we say both of these are equal to the same constant lambda, and this leads me to two eigenvalue problems. So I get two eigenvalue problems as before. And those two eigenvalue problems are x double prime, I put the minus sign over here. So let's do this. So this is x double prime minus lambda x equals 0, and y double prime plus lambda y is equal to 0. And you might say, how did I know which side to put the minus sign on? How do I know where to put the minus sign in this expression? Well, you're about to see that, if I actually look at the boundary conditions here, what does this lead to? Right? Well, the boundary conditions, this boundary condition leads to the BC in the eigenvalue problem, x of 0 is equal to 0, and that's the only one we get, right? Because the other boundary condition is not homogeneous, so I don't get like a homogeneous Dirichlet boundary condition here. For this problem, though, I get 2, right? So for this problem, I get y of 0 is equal to 0, and y of b is equal to 0. So I get 2 Dirichlet boundary conditions for this y eigenvalue problem, and this is why I put the minus sign here, because it's clear from this context I'm going to get the eigenvalue problem I know how to solve on the y. So because of that, I did this sign adjustment thing so that this would be exactly the eigenvalue problem that I know how to solve. This is exactly my list, right? This comes from my list. And so I know how to solve this one immediately, right? So we solve the y problem first, and again, that's because we were able to immediately write out this eigenvalue problem that's on our list of solvable eigenvalue problems. Okay, and then we're going to use the eigenvalue lambda found here to solve this equation. Okay, so let's see what's on my list. Where did I put my list? Oh, I may have thrown my list away. Well, that's no good. Okay, well, at this point, I guess we've seen the list enough that we don't necessarily need it, but refer to the list, right? So I've shown it on camera enough that we know it by now, so refer to the list. This is my eigenvalue problem with homogeneous Dirichlet boundary conditions. So I know exactly what that thing looks like. Here the length of the interval in question is b. And so, what does this thing look like? The eigenvalues are lambda sub n, which is n pi over b squared, and that's for n equals 1, 2, so on. And eigenfunctions are y sub n of y, which are the corresponding sine eigenfunctions, so sine of n pi y over b. So there's my eigenvalues, there's my eigenfunctions. Now, we use these to solve the other eigenvalue problem. So we use these eigenvalues to solve the other eigenvalue problem. The other eigenvalue problem, of course, is this one. Okay. And so this eigenvalue problem becomes x double prime minus n squared pi squared over b squared. X is equal to 0 with that single homogeneous condition, x of 0 is equal to 0. So this is what we're solving. Okay. Well, this is x double prime minus a thing that is always positive, right? X is equal to 0, so these are always positive here. The solutions to this are not sines and cosines, they're exponentials, right? So the solutions are exponentials. So solutions are exponentials. But it is convenient to remember that exponentials can be written as linear combinations of sinh and cosh functions. As linear combinations of hyperbolic sine and cosine functions. Sinh and cosh. Recall that the cosh of square root of lambda x is e to the square root lambda x plus e to the minus square root lambda x over 2. And sinh is square root lambda x equals e to the square root lambda x minus e to the minus square root lambda x over 2. So if it's been a while since you've seen these, here's a quick refresher. Okay. The analog, so the analogy between cosh and cosine and sinh and sine is pretty strong. Cosh is an even function, sinh is an odd function. Cosh of 0 is 1, sinh of 0 is 0. The really nice thing, of course, is that the derivative of cosh x is sinh x, and the derivative of sinh x is cosh x. No need to remember a minus sign here. Of course, you could just check that directly. Okay. And so, you may have even, in 246, you have these recipe formulas for the linear systems case. And oftentimes, these are stated in terms of these fundamental solutions that involve cosh and sinh anyway. So in a sense, everything you're doing when you're first solving like second order scalar ODEs, everything could have been formulated in terms of cosh and sinh when you're in the exponentials case, because you can see how writing these as linear combination, you actually recover just the exponentials you're looking for. Anyway, you might say, why would I do this rather than just writing like constant times exponential plus constant times the exponential to another exponent? Sometimes it is more convenient to write it in this form, and this is because of the boundary conditions, basically. So the boundary conditions make it slightly more convenient to write it in this form. And so we can do this. Now, for this eigenvalue problem, the whole reason for doing this is because I can write that the general solution is x. So this is x sub n of x is c1 e to the, so the general solution is c1 e to the square root of lambda n x plus c2 e to the square root of lambda n x. But I'm going to write this in terms of cosh and sinh instead. Okay, so instead, we write this as x sub n of x is c1 cosh of square root of lambda n x plus c2 sinh square root of lambda sub n of x. Okay. All right. So if we write this out, this would be c1 cosh of n pi x over b plus c2 sinh of n pi x over b. But we have a boundary condition that we haven't imposed yet, which is this one, right? Is this one. So recalling that this is the general solution to this eigenvalue problem, x of 0 equals 0 implies what? Well, if I plug in 0 here, cosh of 0 is 1, sinh of 0 is 0, so sinh of 0, that this term goes away. And I have c1 times 1, so c1 has to be 0 here. Okay. Thus, our separated solution takes the form u of xy, which we have written as, and maybe I should write this as u sub n of xy. This takes the form of x sub n of x, y sub n of y. But we just found that x sub n is really this sinh term, and y sub n is the sine term. And so our separated solution takes the form sinh of n pi x over b times sine of n pi y over b. Okay. And so, how does this help me? Well, what was the process at this step before? Right? So what was this process before? So now I claim my solution to what was the problem that we were solving originally. Let's go back and look. It was this one that had three homogeneous boundary conditions everywhere except this last one was not. We called this star. So my solution to star is given by a linear combination, an infinite linear combination of these eigenfunctions, this separated solution like this. So u of xy is equal to the sum from n equals 1 to infinity of some coefficient c sub n times sinh n pi x over b times sine of n pi y over b. Okay, where the c sub n's are going to be chosen in such a way that solve the I called it an initial condition, but it's really the last boundary condition. So the question is, can I choose c sub n in such a way that my inhomogeneous boundary condition is satisfied? But what does that mean? I.e., Recall, the inhomogeneous boundary condition is this last one, so u of ay has to be equal to f of y for y between 0 and b. So I want f of y to be u of ay. And so what is u of ay? That is the sum from n equals 1 to infinity of c sub n sinh of n pi a over b sine of n pi y over b. Okay. So can I find coefficients c sub n that make this expression hold, that this function f of y I'm given as my boundary condition function here for this piece, right, the right end, can be written in this form? And the answer is yes. The answer is yes. How can I do this? By finding the Fourier sine coefficients and this is for f of y, and dividing them by this extra term, right? So let's look at this. If this term wasn't here, then what I'm dealing with is just the question of writing this as its Fourier sine series, right? So then the only difference between this and this is the fact that I have this stupid extra sinh of n pi a over b term. So you can rewrite this, right? Reformulate this if you like. Call this big A sub n, okay, or b sub n or something like that. Now you could find the Fourier sine coefficients for this thing, which is going to result to dividing through your result by sinh of n pi a over b. Okay, and so, and dividing them by sinh of n pi a over b. And to see how this works, so I seek, so the Fourier sine coefficients, recall, Fourier sine coefficients of f of y are given by 2 over the length here, which is b, times the integral from 0 to b of f of y sine of n pi y over b dy. Thus, the c sub n that we seek is just 2 over b times sinh of n pi a over b times the integral from 0 to b of f of y sine of m pi y over b dy. So if I choose these c sub n's as my coefficient, the solution to star is u of xy, which is the sum from n equals 1 to infinity of c sub n sinh n pi x over b sine n pi a, or sorry, n pi y over b, where the c sub n's are given by this formula. Okay, so this, the solution to this is given by this solution formula. So it went mostly the same as it did before. The only difference really is that, of course, the boundary conditions were a little trickier because the boundary was trickier, right? The boundary is just bigger dimension-wise, right? It's no longer two endpoints. So anytime you're dealing with spatial variables or spatial dimension that's higher than one, right, you're going to have a boundary that's a little bit more complicated than just two endpoints. Okay, and so you're going to have to worry about that at some point if you're dealing with these higher dimensional problems regardless. But, you know, so we see that it very much mattered what the specifics of the boundary conditions were, how I defined these things. And of course, I didn't solve the most general problem, right? I only solved this one. If I wanted to solve the most general problem, I would have to do this process 4 times, right? One for each of these inhomogeneous slots. Okay, and you can think about how that would work and how that would change what happened. But ultimately, it was very similar in this case, at least, right? It was very similar. Okay, so now let's consider Laplace's equation in a disk. Now let's consider Laplace's equation in a disk. So how do I state this? So consider the BVP, and you can call this like the second example of Laplace's equation that we're going to do if you want. So consider the BVP that is given as follows. Laplacian of u is 0 in for x in D, right? Where we might as well make this some disk, say, centered at the origin of radius A. So we'll say this is radius A. So what's the way of describing this, right? And this is the closed disk. This is not just the circle, right? The circle is its boundary, but this is the entire closed disk of radius A. Okay, so this is the set D, which is described as the set of ordered pairs xy in the plane such that x squared plus y squared is, we'll say that D is the open disk and the boundary is the circle, right? So here's my boundary, which is the circle. Of radius A centered at the origin. Okay. All right. And so I'm seeking a solution u of x. I'm writing this as a vector now, such that the Laplacian of u is 0 for x in D, this disk. Right? So maybe I'll rewrite it here just to do it. So set of order pairs xy such that x squared plus y squared is strictly less than a squared. So that is the open disk of radius A centered at the origin. And u is equal to some function, we'll call it h, on the boundary. Okay, so this is, again, a Dirichlet problem for Laplace's equation on the disk. So I have a prescribed function that's my data function on the boundary, right, on this circle. In the interior, of the circle. I seek a function that is that prescribed function on the boundary and is 0, right, inside. Now, when we first, or it's Laplacian, sorry, is 0 in the interior. When we first talked about Laplace's equation, I mentioned that the process here was like trying to think of, you have harmonic functions on a region, so in this case a disk, right? And you're trying to match those harmonic functions, I think we called them designer functions, that had a prescribed value, right, as a function on the boundary of the region in question. So that's exactly what we're trying to derive here, right, in the case of a disk. Okay. Now, I want to use separation of variables, but for a variety of reasons, when you look at a problem like this, and you might remember from Calc 3, almost any time you were doing a problem that involved a function of two variables over some region that involved disks or parts of disks or annular regions or things like that, it was almost always useful to do these in polar coordinates instead, since in polar coordinates, this is a rectangle, right? So in polar coordinates, this this thing in the r theta plane, right? This is a rectangle. So if we're in the xy plane here, in the r theta plane, this is a rectangle. And hey, we just solved it for a rectangle, so maybe that would help us. Well, even if we don't directly reference that, this is kind of the thinking, right? Or this is one motivation for why you want to why you want to move to polar coordinates when you have something involving disk. It's just that it's easier to describe this way. Look at how complicated relatively it is to describe this region, but this is a fundamental region, right, in polar coordinates, and it's very easy to describe. And so, what do I do here? So first, I change to polar coordinates. Or, yeah, so I'll change to polar coordinates first of all. If I let u be a function now of r and theta, instead, how do I describe my boundary in these new polar coordinates? This is described as like r theta such that r is equal to a, right? R equals a is the equation that describes that boundary circle. R being strictly between 0 and a describes the open disk, right? So another way of rewriting this is to say that, so u equals h on the boundary implies like u is h of theta on r equals a, right? All right. Now, what is the Laplacian in terms of our new coordinates? So recall, this is like an exercise from the Laplace's equation chapter. Laplacian of u in these new coordinates can be written as u sub r plus 1 over r u sub r plus 1 over r squared u sub theta theta. That is the Laplacian in terms of polar coordinates. Okay. And so we have an equation. Laplacian of u is 0 on d. D is going to be, in polar coordinates, d is just r. If we say that r is always positive, this is just saying that r is less than a. And so I can really conveniently recast this equation using polar coordinates. So in polar coordinates, my equation which I'll just rewrite as Laplace U is 0 on D and U equals H on the boundary, becomes the following. So Laplacian is this thing, right, in polar coordinates. So this becomes U sub r plus 1 over r U sub r plus 1 over r squared U sub theta theta is equal to 0, and that is for r strictly less than a. And u is this function h when r is equal to a. And so this is the thing that I want to solve. Okay. So now my idea is to use separation of variables on this equation. Okay, so I want to use separation of variables on this rewritten equation. Okay, so if I do that, i.e., I seek a solution u of r theta that can be written as the separated solution r of r times theta of theta. Okay. So then I put this into the PDE here, right? So PDE implies what? Just plugging this in, right? The r partials only hit big R, the theta partials only hit big theta. And so what I get here is an equation that looks like r double prime big theta, right, plus 1 over r prime big theta, plus 1 over r squared r theta double prime is equal to 0. Now, if we divide both sides by r theta and multiply by r squared, so simultaneously, what do we get? We get r squared r double prime over r plus r times r prime over r is equal to, I'm going to put the minus sign on this side, so this is minus big theta double prime over big theta. And we have on the left-hand side something that only depends on r. On the right-hand side, something that only depends on theta. And so by the same analysis that we always do, this is equal to some constant lambda. Okay. Now, there's some slight issues here. There's some slight complications here before we proceed any further. I'm going to get my eigenvalue problems in the same way here, right? So I'm going to get my eigenvalue problems, but the question is, what are the boundary conditions going to be? Right? What are the boundary conditions going to be? Well, the only boundary conditions I have they come from here, right? Well, that has to be used for my initial conditions somehow. But how does that make any sense? How does this work? Well, Hmm. Hmm. So what is good here is let's look at the actual equations that we get, right? So what eigenvalue problems do we get here? We get r, so we get eigenvalue problems, and this is little r squared times big R double prime plus r prime minus lambda r equals 0. That's one of them. Okay. The other one that I get is going to be my usual eigenvalue problem. But what are my boundary conditions? Well, the problem is that this is not going to help me with these boundary conditions because this thing needs to play the role of my initial conditions to determine like the Fourier series coefficients that I'm going to have to use to make all of this work. So I'm stuck with two eigenvalue problems, but it doesn't seem clear that these have boundary conditions that I'm going to be able to use from this problem statement. But you may be, screaming at your computer now because you've noticed, oh wait, this switch to polar coordinates actually carries some boundary conditions into it, right? These boundary conditions are implicit, right, in this formulation here because of how polar coordinates work, right? So what about the BCs? Note what happens here because of this formulation is that big theta of 0 has to be big theta of 2 pi. And big theta prime of 0 has to be equal to big theta prime of 2 pi. Why? This is purely from polar coordinates and what theta means, right, as a variable in polar coordinates. These two things have to match. And so we have periodic boundary conditions. And these boundary conditions didn't even come to us from like the prescription of this H, right? It came to us implicitly via polar coordinates. Well, I know what my eigenfunctions are for periodic BCs. This is the full Fourier series, right? It's the coefficients corresponding to the full Fourier series. And so let's do the theta one first, obviously, because this looks like a nightmare at first. But this is exactly the eigenvalue problem we've always had. And now we have, after we've thought about it for a bit, we have these boundary conditions. And hey, periodic BCs, that's on my list. Right? That's on my list. And so this implies that solving the theta eigenvalue problem first, I get eigenvalues. So let's think here about my eigenvalues here for this thing. What are my eigenvalues? If this is n squared over, so let's think about this, right? If this is in terms of the usual formulation, this is going to be lambda n equals n squared. Because this is full Fourier series, I can state this for n, so that my eigenvalues are for n equals 0, 1, 2, and so on. The eigenfunctions are big phi sub n of, or sorry, big theta sub n of theta is equal to a sub n cosine of n theta plus b sub n sine of n theta. And we'll say this is for n equals 1, 2, 3, and so on. And then for n equals 0, my big theta naught of theta is just constant a naught. Okay, this means I can write those in a single Fourier series listing coefficients like this without having to break them down into cases. So there's my eigenvalues and eigenfunctions. Okay. So then I need to now use those eigenvalues in my other eigenvalue problem, as I always do. Right, and so what do I get here? This is r squared, so other eigenvalue problem. I have r squared times r double prime plus r prime minus n squared r is equal to 0. Okay. And so how do I deal with this, right, where n is 1, 2, and so on? How do I deal with this? You may remember the name of this. Depending on your instructor, this might not have, its name might have never been uttered in your ODE class, but the great thing about this is that this is an example of a variable coefficient ODE that you can actually write the solution of, because it satisfies a very nice fact, namely that the variables are polynomial and the degree in each term agrees with the order of the term. So r squared on the r double prime term, r on the r prime term, and then there's no r showing up here. This is an example of what's called a Cauchy-Euler ODE. Okay, which is a very important class of variable coefficient ODEs, and one of the biggest reasons why it's important is because it's one you can actually write down the solutions of, right, which is very, very nice. Normally, you need to find the solutions of variable coefficient ODE. None of the usual techniques that you learn in a first ODE course will work, especially not in general. And so you need to rely on the fact that this is a special one. And in this special one, what is the idea? What is it that you do for an ODE like this? You notice that you seek a solution of the form big R of R is R to the alpha for some exponent alpha. Okay. And when you do this, plugging this into the ODE and figuring out how you would need to choose alpha to make this all work out, if I plug this into the ODE, so here I'm going to, let's see what I would do if I differentiate this thing twice here. This would be R. So if I differentiate this thing twice, I would have alpha times alpha minus 1 times r squared times r to the alpha minus 2 plus alpha times r to the alpha minus 1 minus n squared r to the alpha is equal to 0 But then, what do I get here? I get alpha times alpha minus 1 times r to the alpha, right? R squared times r to the alpha minus 2, plus alpha times r to the alpha minus n squared r to the alpha is equal to 0. Doing some algebra here, what has to be the case? So the only way that this can happen is, let's get rid of the r to the alphas. What I'm what I'm left with is alpha squared minus n squared has to be equal to 0, which means, of course, alpha is plus or minus n. Those are my options. Thus, I get eigenfunctions r sub n of r of the form c sub n r to the n plus d sub n r to the minus n. And you can check that each of those will solve this ODE here. Okay. Now, let's go back to our problem that we're looking at. Okay. So let's go back to our problem that we're looking at, and let's think whether or not these things make sense. What do we want to happen? So we're not excluding like the origin here on this disk, right? Like we want you to have, we want it to be at least continuous at 0, right? We want it to be defined and continuous at 0. And so if we want it to be defined and continuous at 0, then I have to get rid of terms like this, which would cause problems because at the origin r is equal to 0. So I want those to go away. I want to set d sub n equal to 0 here, right? Because it's like that's going to be a problem here. If lambda, if the eigenvalue we choose is the 0 eigenvalue, then what do I get? What do I get in this expression? In this expression, I would get a function that's like c naught plus d naught ln of r instead, right? The log of r. But again, that would blow up at r equals 0. So we have to set this equal to 0 for all n, right? Equals 0, 1, 2, and so on. Okay. And all of this is just so that the resulting function we get agrees with, if we want this thing to be a solution to Laplace's equation, we want it to have continuous second order partials of all type. And if we wanted to have that on D, right, our open disk, then particularly at 0, we want it to satisfy that. Okay, and so that's why we have to get rid of, disallow solutions like that. And so our admissible solutions, we can set the c sub n is equal to 1 if you like, because these are eigenfunctions, they're going in a product, and there's going to be coefficients. Anyway, so the eigenfunctions in question that we end up taking are these r to the n's, right? These end up being the ones we want. Then we have our separated solutions for each n. So u sub n of r theta is, r sub n of r, big theta sub n of theta. And then my solution then is u of r theta, which is the sum, right, from, we'll do it from n equals 0 to infinity of these separated solution. So I have this countably infinite sum. I'm going to separate out the n equals 0 term. So this is going to be 1/2 a naught for the same reason as always, plus the sum from n equals 1 to infinity of r to the n times a sub n cosine of n theta plus b sub n sine of n theta. Okay. All right. Now, we are almost done here, right? So I want to impose, right? So now I want to impose my BC, which if we go all the way back to this polar coordinates problem, is that u should be equal to h of theta when r is equal to a. Right? So at r equals a, h of theta should be equal to 1/2 a naught plus the sum from n equals 1 to infinity of here a, if r is equal to a, this is going to be a to the n incorporated here. So this is like little a to the n times a sub n on cosine n theta plus little a to the n times b sub n on sine of n theta. Okay. And so using our usual Fourier series analysis here, this means that these Fourier coefficients a sub n can be obtained by dividing the usual full Fourier series coefficients by little a to the n. So this is 1 over little a to the n pi times the integral from 0 to 2 pi of h of theta cosine of n theta d theta. And b sub n is 1 over a to the n pi times the integral from 0 to 2 pi of h of theta sine of n theta d theta. Okay. And so this is what I get. Here's my solution. And these coefficients are determined in this way. And this might seem like a very convoluted way of going about this, but we'll see how this can be put back into rectangular coordinates next time to give us our final form here, right? So next time we'll go back to rectangular coordinates and see what this formula looks like. So we'll do that at the beginning of lecture tomorrow. Okay. So anyway, that's kind of our immediate goal. And after we see that, it turns out to work out rather nicely. After we see that, we're going to branch out into some of these other generalizations of separation of variables algorithms and kind of see what happens when you move a little bit beyond, right? What happens when our canned list of eigenfunctions is no longer adequate and we need to expand these to a slightly broader class of functions. We'll see a little bit of what that looks like, and I'll give you some examples that show up in a variety of contexts such as physics and other types of analysis. So we'll talk about Bessel functions, we'll talk about spherical harmonics, those kinds of things. Okay, so that's where this is headed, and that's a nice kind of ending point, I think, for rounding out this material. But anyway, we're gonna be doing more of this stuff tomorrow, so I will see you all then.